Blasphemy?
Yes.
Oh well, let's see what happens to me. Okay.
Sacrilege.
We'll see if some tribe comes up and tears my heart out. What was that in Indiana Jones? My mom got them all. No. All right, let's leave that behind. So no questions from homework?
Can we do questions from the test?
Sure.
How do you do the third bonus?
See if I have anything left up here. Here we go. Last test one. Which one? Oh yeah. So that's the one you got to draw the triangle that's represented by the inverse cotangent. Draw the triangle. So, see if you guys remember this from last time. If I said inverse sine of y over 7, what triangle can I draw that angle represents? Or
7 is the hypotenuse.
Yep.
And y is y.
Y is y. Kick ass, because it's sine, and sine likes y. Screw Sokotoa, it's special shit. And then I can ask you whatever, right? I can ask you, alright, so what's the tangent of this? Tangent of this angle.
It's x over y, so
So you have to figure out this side, which is
Square y squared minus 49. 49 minus y squared.
so you get y over that for tangent, right? You guys kind of with me? Inverse trig functions represent angles. Those angles can be housed in triangles that actually could physically not exist, but the math doesn't give a shit about that. We know that by now. It's this triangle I draw could actually physically not exist for any values, but the math doesn't care. Any real values, but then we know we can get imaginary stuff. Why not? You can always draw a representative triangle for any given inverse trig function. Always. And then if I ask you a specific other trig function of that angle, you just finish the triangle and tell me. Alright, so that's a leftover thing from pre-calc that your pre-calc teacher should have went over decently well because they should have known that it was going to hit you in calculus, but if not, you'll find him, slap him. Alright, anything else from anything?
46, 3.5.
Homework question? What the hell?
I mean, I started it.
Ooh, I like it. Show that the sum, alright. The sum of x and y intercepts of any tangent line to this curve is equal to C. Now I know it's obvious by just looking at it this is true. No, it's not obvious. So where would you start on this problem? I mean, again, this is number 46, 3.5.
Finding tangent line.
Yeah, so this is how you look at a problem like this. You have to realize the people that are really good at math are the people that kind of naturally break things into parts. If you don't naturally do that, you got to force yourself to do that, right? I'm not naturally good at painting. I can force myself to paint something. I can force myself to learn techniques. I'm just not naturally good at it, but I can do it. I've done it. I'm not going to show you guys, man. So how do I find any tangent line to this? It's the same question as always. I just have something that's written in a way that I have to use what kind of differentiation? Probably the title of the section this sits in, right? Implicit. I like it. So if I rewrite this to look a little better, what would it look like? Equals, who cares? I can leave that because square root of C is what?
constant.
Constant. Kick ass. Ouch. And then how do you take that guy's derivative?
1 over 2 x minus 1.
Yeah, the 1/2 comes down, it goes down by 1. Now the same thing happens here, except the inside function. Right, this is times dx, which is 1. But this will be times dy dx, which of course I don't know, so I gotta leave it there. Equals 0. And solve for dy dx. It's a really good first step. I don't want to go too far in this problem because I get this sense that not all of us have looked at this problem yet. So that's this part. And now it's talking about the sum of the x and y intercepts of any tangent line. So now I got to figure out what's the formula for the tangent line. Any tangent line. Oh shit. That'll get interesting. So any tangent line at any point on this line. So what you could do, let's do a specific example. What about at the point, let's see, if x were 1, what would y be?
0.
This gets weird. If x is 1, what would y be? Y would equal to square root of c minus 1 square. Right? You guys with me? So there's your point. What's my slope at that point? You can plug it in and figure it out, right? I like it. But you're supposed to do any point. So I'm going to adjust this a little bit. Let me at least help you this far. There's got to be any point on this line. So maybe I'll use the point x1 and square root of c minus... Well, you got to be careful now. If it's x1, what's y equal? So that is what would be here. That would be the point you're interested in. So I got a point. I need the what to get the equation of the line. Point and the slope. I love this one. So freaky. So I'm going to let you guys get to that and try it out. Maybe ask me again tomorrow. We'll see if I feel like I should do any more. If anybody else actually tries it. If that's the only problem you're having trouble with in that section, you're doing really good. You're doing great. You're doing fine. The rest of you guys don't know yet. Get in there and do it. Okay. Anything else from homework? Okay. What was it? Somebody asked a question. I don't have a question, but yes.
You do 66.
Okay. Oh, good. I had somebody ask me about this. That one feels like this in a way. It's equally vague. Has everybody got what they want from this? Okay, sure.
Yeah.
I didn't want any of it, Jeff. And yet you gave it to me. Yeah, that's the way it works. All right. I love it. So I don't know I think I said this at some point. The word perpendicular, there's a lot of words. And then we said normal is another way of thinking about perpendicular. And now yet another freaking word. Orthogonal. All right, looks like it's going to be some kind of bug killing thing, right? Orthogonal. And they got orthonormal stuff and stuff. You're going to take linear algebra. It's going to have all kind of ortho blah, blah, blah. Two curves are orthogonal if their tangent lines are perpendicular at each point of intersection. So if I had a curve like this and I had a curve like this, if they meet right here at a right angle, right, and that's the only place where they intersect, then they would be orthogonal curves. How are we doing so far? If you've taken any physics, you can think about electromagnetic waves and how the magnetic part and the electric part are always at right angles to each other, right? Maybe that has something to do with this, maybe. If you're not physics, don't worry about it. All right. And they ask us to show that the given families of curves are orthogonal trajectories of each other. Every curve in one family is orthogonal to every curve in the other family. So at every point that they meet, they are perpendicular. And what's perpendicular mean?
Negative reciprocals.
Good. The slopes are negative reciprocals of each other. Sounds very useful, right? So the curves they give me, what was it, AX and BY? now, if I just put a number here, what kind of curve is this? If I draw this, what would it look like?
Circle.
For almost any number, I can't pick 0 or negative numbers, right? That would be freaky. It'd be a complex plane or just a dot. X equals 0 would be 0, 0, just that dot. It's still a circle, but can anybody tell me what kind of circle it is now? Like the first one. What the hell's going on there? Can you guys reason that out? Which variable would you have to complete the square for if you wanted to solve this?
For x.
I'd have to complete the square for x, which means the y would stay at 0, but the x is going to, well, not jumping down, the x is going to move, right? So this would be a circle that's been moved by some amount over or back, and this would be a circle that's been moved up or down, right? Okay, so that's what's going on here. So what this is saying is, if these two circles meet at any points, that they would be orthogonal at those points. They would be perpendicular at those points. That's what this is saying. Okay. So it sounds remarkably daunting. You're like, do these people realize I'm in Calc 1? Do they realize that? I'm like, yes, we do. Still do this. What's a really, really good first step considering the whole idea is about the slopes of these? No.
Equal ax and y.
Yeah, good. So there's two kind of competing things going on. I want to find the slopes, and then the other part of this is the slopes have to do a specific thing where these two meet. And when do these two meet? That's pretty easy.
Well, they equal each other.
True. And when does that happen?
Ax equals by.
AX has to equal BY, and then these would meet. Is that cool? So there's one fact we got already. AX must be BY. That looks remarkably useful, and it looks fantastic. That looks much better than anything else up there. And then the second thing you could do, that I'm not going to do now because I was going to do one of these and you already said that, is take these guys' derivatives. And then try to do something with that. You know, everywhere they meet, you got to show that the slopes are negative reciprocals of each other. Okay, that's all you need for that problem. This problem's a lot easier than it sounds. It looks disgusting. I'm like, what the hell is A and B? It's just some numbers. Any numbers I want them to be, almost. Except negative. Those inverse circles. Circles in another dimension. You good? Alright. Anything else? Those are definitely two of the freakier problems in that section. Okay. So let's just do a couple of review problems from implicit differentiation. And then I want to show you some stuff up on the board here. Or up on the, using Wolfram Alpha. Oh yeah. Wolfram Alpha, one of the most immediately nice things with Wolfram Alpha is, I'm going to teach 281 next semester, and whenever I do that, I definitely have my Wolfram Alpha account up to date, because then I can plot three-dimensional figures and turn them around. So when I took Calc 3, I had my teacher who drew about as well as I do, trying to draw three-dimensional figures on the board. Holy shit, we were all like, what's that? What's that? You know, so now we can just do it live. We'll do it live. It's crazy on the computer, so it looks all nice. So let's look at this. This is the one I want to show you on the computer. Let's see, where'd it go? I can remember what it is, so who cares? Can you find dy dx for that? Where'd you go? It's here somewhere. There you are. So if you weren't here last time, you're like, what the hell? What the hell? Well, let's see. How do I do it? What fundamentally is going on there?
Product rule.
Product rule. So the derivative of x is
1
times sine y plus x times the derivative of sine
that's cosine.
cosine
That's d1 dx.
times dy dx. Very quickly, something that's driving me a little insane. Don't even write this down, just is there any difference between those two?
Yes.
Oh yeah. Oh yeah. But some of us seem to think that cosine can exist without anything in it, and that's impossible. You just have cosine like you divide both sides by cosine. Right? Just that's happening. Don't do that. That should not be something you can physically do. Right? You wouldn't say, how do I solve this? Well, you divide by the square root symbol. There you go, Jeff. So x equals 7 divided by the square root symbol. And you haven't taught us what that is yet, Jeff. Screw that shit, right? Come on now. We're better than that. So stop it. Alright, that's my rant at the moment. So that is all this. And now I have something that looks very similar over there, right?
dy dx.
Yeah, dy dx. Sine x. Good. That's the first part of product rule. Plus, leave y alone. Cosine x. Times dx dx, which is 1, right? The inside function is x, so it's going to be 1 equals 0. And now this step is pure algebra, right? Dy dx is a variable in a way, right? So then you can solve for it. So what do I want to move over?
Sine y
Sine y,
and
y cosine x, and in the process I can take dy dx out, right? What's in here?
x cosine
X
y
cosine
sine x.
And then divide by the stuff I don't want. Let me write this over here. So I'm going to do something really freaky, as always. Okay, let's capture what we got here. So we got dy dx equals negative sine y, become an n of y. There you go. Minus y cosine x over x cosine y plus sine x. See the symmetry that... I don't know if you guys see what I mean. That's what I mean. There's a minus y cosine x. There's an x cosine y. There's a sine, negative sine y. There's a positive sine x. Very often, not always, when you do implicit differentiation, you get these kind of like mirror images or symmetries or something going on. Anyway, all right. So what I want to do is I want to go a little bit beyond this problem, but there are problems in this section like what I'm about to do. And we desperately have to do this to get ready for something coming up to us down the road. I want to redo this whole thing, except I want to find dx dy. Oh shit, so then what am I taking the derivative with respect to?
With respect to y.
With respect to y. So then the derivative of y will be
1.
1. Oh shit. Let's try it. Because everything we've done so far is arbitrarily dy, dx. Math doesn't give a shit which one you consider to be independent versus dependent variable, and it doesn't care. So I should be able to, okay Jeff, forget the idea. I should be able to turn that around. So let's try it.
So what times dx dy?
And this is why this notation becomes so much more important than the prime notation, even though it leads to stupid transformer jokes, is because you can keep track of what you're actually taking the derivative with respect to. Prime, you don't know, it's just prime, it doesn't tell you anything. So when I see an x now, what's the derivative of x now? I'm taking it with respect to y, so it's going to be dx dy, sine y, plus x. And what's the derivative of sine y with respect to y? Let me write it like this. I'm going to write out the rule. So now, what is my implicitly defined function? Before it was y is a function of x. Now it's, of course, x is a function of y. And you can always, if I have y equals x minus 1, that's y is a function of x. X equals y plus 1, that's x is a function of y. Ooh, who gives a crap, right? The whole way we do slopes could have been turned around. We could have done always run over rise. Totally could have, but we didn't.
Can I ask you a question?
Sure.
Isn't it 0?
0, yeah, thank you. Shoot. So here, that's done. dx dy sine y plus, what's d by dy sine y?
Cosine.
Cosine y. Because then it would be times dy dy, which is 1. The same reason why dx dx is 1. The same reason it doesn't show up then. So I'll have x cosine y plus, of course, d by dy y,
Sine.
That's 1.
1 times sine x, plus, what's d by dy sine x? Derivative of sine is
That's cosine.
cosine. Derivative of the inside function, chain rule,
Dx dy.
dx dy equals 0. Thank you, John. Something really nice is going to happen here at the end. Believe it or not. So now, just like before, I can subtract that stuff over. I can take dx dy out. And then I can divide by this stuff here, right? Oh, minus. Thank you. So I subtracted that stuff over, took a dx dy out, divided by this stuff that I don't want. Thankfully, how does dx dy compare to dy dx?
The singularity reciprocity.
Say again? They're just reciprocals of each other. Thank God. You would hope to God that dy dx, if you reciprocate it, you should get dx dy. Whatever dy dx is, if you want dx dy, you just flip it. You guys understand what's happening? Thank God.
Yeah.
It's always true. It's really nice. It's really nice. Okay. So there are some problems in here, though. They want you to find dx dy. I want to force you to do it this way. But if you're not really totally comfortable, you can try to do this and then just see if you get the same thing if you flip it over, if you want to do that. But you need to get used to looking at it like this.
You flip it and then times it by -1?
No, the negative just moved, the negative's on the top here, it's still negative, but they're exactly equal to each other flipped over. Is that cool? It didn't change the sign. That's negative, and so is this. I like it. Cool. Maybe. All right. Let's see. Oh, let's do this. Only I was excited about this. Be quiet. No. Stop. So here's the function we just did. Right? Wow. So I just put it into Wolfram Alpha. Wolfram Alpha kicks so much ass. It's amazing. So you could never put this into your calculator, right? In order to put it in your calculator, what would you have to do first?
Solve
for y. Holy shit. Cannot do it. Impossible. Fundamentally. You can sort of do something, but it gets all freaky. So the image I'm about to show you, is this a function then? Is this truly a function by the definition of function? If it is a function, I should be able to solve for y. That's the fundamental idea of a function. If it's a function of x, I should be able to solve for y, so I get a function of x. I can't. Therefore, I should expect my graph to totally not pass the vertical line test. Or maybe horizontal, who cares? With the vertical one, it's not even a function. So here's what it looks like. I love this. Look at that. And you're all like, the crowd goes, meh. But what's really cool about this that we can't even get to, and that I forgot how to even do in Wolfram Alpha, I got to remember before next semester, is this is just a slice of a three-dimensional object. Normally we have functions that are functions of one variable, right? In fact, this is the title of this class is Single Variable Calculus. Calc 3, you deal with functions of many variables. So if I said this is z here, for the third dimension, I just have to remember the right It's not just plot 3D. Let me try that. I don't think that's it. That's what it does. Computing. Oh well. So it's doing a lot of cool shit. Oh, look at all that. It's partial derivatives. Sorry. Anyways, it won't do it. I gotta remember the right way to format that. But it's one slice. It's where that equals 1. You can say, where does it equal 0.9? So I can go back and say, okay, what if it was equal to 0.9? What would that look like? Probably almost the same as 0.1 did.
Okay, change the front.
Oh, yeah, get out of there. Plot 3D. Thank you. Sure. Do it. You know what I mean? Let's make it 0.2. Let's see. There should be a bigger change. This is a different slice. There you go. You can see the differences there, right, can you? This is definitely a lot tighter in there. These look the same. Right? Okay, maybe. All right. That's really cool. If you think about it, it's a three-dimensional object. I'm just slicing at these different levels. Z equals 1. Z equals 0.2. Right? I'm just slicing it. That's just one slice of it. Okay, that's enough of that. Okay, so Wolfram Alpha is really a great place to go get a feel for what some of the stuff looks like if you want to. Okay, so what I want to do now, if there's no other questions from that section, I want to finally figure out what the derivative of natural log is. Okay, so you guys know it. What do we do? Oh yeah, it comes later. 9. Man, it takes a while to get there. Oh, here we go. Good. So we'll do ln right now, and then we'll back up and we'll do the arc trig functions, the inverse trig functions. Right. So how the hell am I going to do that? So if I want to know, here I got y equals ln x, and I want to know what dy dx is. And let's say I don't know. Even if you know, we officially do not know, according to where we are in the book.
Using D?
Yeah. So just like if I had an area that I didn't know, so I like to show people if you cut a circle up, and if I don't know the area, you can actually cut it, open it, rearrange it to be this. You can do it, Jeff. You can rearrange it to be a rectangle. If you put those teeth in together, I don't know, I did that really quick, but you cut a circle, you open it up, open the bottom up, you can figure out what the area is because I've reformatted it into an area that I know. So here I don't know this derivative, so let me reformat this into a function that I know the derivative of. So how do I rewrite this? X equals what?
X equals EY. EY.
E to the y. Is that cool? And now I know this derivative. Now that I know implicit differentiation, I know how to do this.
So, 1.
In fact, well, let's see. Well, let's just do this directly first. What's the derivative of x?
1.
Dx? Yeah, 1. And what's happening here?
EY.
E to the y times
DY dx.
dy dx. I like it. So what's dy dx?
1 over
Over
EY.
E1.
And what was e to the y?
X.
X. There you go. So dy dx equals 1 over x. You can do it, Jeff. So now we know the derivative. If I have y equals ln x, y prime is 1 over x. Kick ass. I like it. So ln is sort of the bridge between the two sides. If I take derivatives of x squared, can I ever get to the negative powers doing that? One derivative would be 2x, another derivative would be 2, another derivative would be 0, and then it's 0 forever. Oh, there's no bridge. Yes, ln bridges the negative powers with the other side of things, sort of. Right? Not as nicely as we hoped, but oh well, too bad. ln has to come in there somewhere and get something done. Alright, so that's this. So let's immediately use ln in some more funky ways here. If I had f of x equals ln of 1 minus 2x cubed, find that guy's derivative. Now that we know this rule. That's cool. Sorry. It does implicit differentiation. Isn't that insane? Okay. Some of you guys will look at that and say, oh, Wolf and Alpha will do my homework for me. Yes, it will if you pay money. And then you'll die in the homework and you'll be out some money. Wow. On the test you'll die. You'll lose some money. Kind of sounds like a bad plan. So what is f prime? What's the derivative of ln of anything? 1 over that thing. That's the basic rule of ln. So whenever you take a derivative of ln of who cares, it starts off as 1 over who cares. Good. Chain rule. Do the derivative of this thing.
Minus 6x.
Minus 6x squared. So you can say it's minus 6x squared over 1 minus 2x cubed.